Hello everyone, and this is the chapter 5 that talks about Ethernet. The Ethernet is a predominant LAN technology in the world. It operates in the data link layer and the physical layer. It is a family of networking technologies that are defined in the IEEE 802.2 and the 802.3 standards. It supports data bandwidths that go from 10 megabits to 100,000 megabits. Ethernet relies on two separate sublayers of the data link layer to operate: the logical link control and the MAC sublayers. The logical link control handles the communication between the upper layers and the lower layers. It takes the network protocol data, which typically in an IPv4 packet, and adds control information to help deliver the packet to the destination node. MAC constitutes the lower sublayer of the data link layer. This layer takes care of two main operations: data encapsulation and media access control. Data encapsulation process includes frame assembly before transmission and frame disassembly upon reception. It provides three primary functions: frame delimiting, that provides important delimiters that are used to identify a group of bits that make up a frame; addressing, that provides a MAC address to a frame; and error detection, which contains a trailer with a cyclic redundancy check of the frame contents. After the reception of a frame, the receiving node creates a CRC to compare the one in the frame. If they match, the frame can be trusted to have been received without error. The second responsibility of the MAC sublayer is media access control. It is responsible for the placement and removal of frames in the media, and communicates directly with the physical layer. Ethernet is a contention-based method of networking, which means that any device can try to transmit data across a shared medium whenever it has data to send. However, if multiple devices send data at the same time, that data will collide. Therefore, it will be corrupted and unusable. For this reason, Ethernet provides a method for controlling how the nodes share access through the use of carrier-sense multiple access technology. CSMA process is used to first detect if the media is carrying a signal. If a signal is detected, it means that another device is transmitting. When the device attempting to transmit sees that the media is busy, it will wait and try again after a short time period. If no signal is detected, it will transmit its data. However, this method is not infallible. That is why it uses another two methods to avoid this problem: the collision detection and the collision avoidance. The collision detection monitors the media for the presence of a data signal. If there is no signal, it transmits data. If there is a signal, all devices stop transmitting and try later. In collision avoidance, the device examines the media for the presence of data signal. If the media is free, the device sends a notification across the media of its intent to use it, and then it sends data. To prevent excessive overhead involved in the processing of every frame, a unique identifier called the MAC address was created to identify the actual source and destination nodes within an Ethernet network. This provides a method for device identification at the lower level of the OSI model. An Ethernet MAC address is a 48-bit binary value expressed as 12 hexadecimal digits. The MAC address value is a direct result of the IEEE enforced rules for vendors to ensure globally unique addresses for each Ethernet device. The IEEE assigns the vendor a 3-byte code called the Organizationally Unique Identifier. The vendor must follow two simple rules as shown in the picture. All MAC addresses with the same OUE must be assigned a unique value in the last 3 bytes. And the other one is that all MAC addresses assigned to an NIC or other Ethernet device must use the vendor's assigned OUE as the first 3 bytes. When a computer starts up, the first thing the NIC does is to copy the MAC address from the ROM into the RAM. When a device is forwarding a message to an Ethernet network, It attaches header information to the packet. This header contains the source and destination MAC address. There are many formats that can be used for the address, as shown below the picture to the right. Each NIC in the network views the information at the MAC sublayer to see if the destination MAC address in the frame matches the device physical MAC address stored in the RAM. If there is no match, the device discards the frame. If there is a match, the frame has reached its destination, and the NIC passes the frame up to the OSI layers, where it is decapsulated. At the data link layer, the frame structure is nearly identical for all speeds of Ethernet. The Ethernet frame structure adds headers and trailers around the layer 3 PDU to encapsulate the message being sent. Both the Ethernet header and trailer have several sections of information that are used by the Ethernet protocol. Each section of the frame is called a field. There are two styles of Ethernet framing: IEEE 802.3 Ethernet standard, which has been updated several times to include new technologies, and the DIGS Ethernet standard, which is now referred as Ethernet 2. The difference between these two are minimal. The most significant one is the addition of the start frame delimiter and the change of the type field to a length field in the 802.3. The Ethernet 2 is the Ethernet frame format used in the TCP/IP networks. Both standards define the minimum frame size as 64 bytes and the maximum as 1518 bytes. The preamble and start frame delimiter fields are not included when describing the size of a frame. Any frame less than 64 bytes in length is considered a collision fragment. If a transmitted frame is less than the minimum or greater than the maximum, the receiving device drops the frame, and those frames are considered invalid. The primary fields in the Ethernet frame are the preamble and start frame delimiter fields, used for synchronization between the sending and receiving devices. Second, the destination MAC address field, which is the identifier for the intended recipient. Third, the source MAC address field, which identifies the frame's originating NIC or interface. Fourth, the length field, which identifies the exact length of the frame's data field. It describes which higher layer protocol is present. Fifth is the data field that contains encapsulated data from a higher layer, which is a generic layer 3 PDU or more commonly an IPv4 packet. And sixth, the frame check sequence field that is used to detect errors in a frame. It uses a cyclic redundancy check. The sending device includes the results of the CRC in the FCS field of the frame. The receiving device receives the frame and generates a CRC to look for errors. If the calculations match, no error occurred. Calculations that do not match are an indication that the data has changed, therefore the frame is dropped. The ipconfig command can be used to identify the MAC address of an Ethernet adapter. The displays indicates the physical address of the computer. Depending on the device, the format of the MAC address will differ. For example, the Cisco devices use an hexadecimal format. With the Ethernet, different MAC addresses are used for layer 2, unicast, broadcast, and multicast communications. A unicast MAC address is the unique address used when a frame is sent from a single transmitting device to a single destination device. As we can see in the first image, the host with an IP address requests a web page from a server with a specific IP address. For a unicast packet to be sent and received, a destination IP address must be in the IP header. A corresponding destination MAC address must also be present in the Ethernet frame header. The IP address and MAC address combine to deliver data to one specific destination host, as seen in the second image. A broadcast packet contains a destination IP address that has all ones in the host portion This numbering in the address means that all hosts on the local network will receive and process the packet. Many network protocols such as DHCP and Address Resolution Protocol use broadcasts. A broadcast IP address for a network needs a corresponding broadcast MAC address in the Ethernet frame. On Ethernet networks, the broadcast MAC address is 48 once displayed as hexadecimal. Multicast addresses allow a source device to send a packet to a group of devices. Devices that belong to a multicast group are assigned a multicast group IP address. Because multicast addresses represent a group of addresses, they only can be used as the destination of a packet. The source will always have a unicast address. Multicast addresses can be used in remote gaming, where many players are connected remotely but playing the same game. Another use of multicast addresses is in distance learning through video conferencing, where many students are connected to the same class. As with unicast and broadcast addresses, the multicast IP address requires a corresponding multicast MAC address to actually deliver frames on a local network. There are two primary addresses assigned to a host service, the physical address and the logical address. Both the MAC address and IP address work together to identify a device on the network. The MAC address in the host does not change. It is physically assigned to the host's NIC and is known as a physical address. This means that it remains the same regardless of where the host is placed. The IP address is based on where the host is actually located. It is possible for a frame to determine the location of where that frame should be sent with this address. It is assigned to each host by a network administrator based on the local network that the host is connected to. A source device will send a packet based on the IP address. One of the most common ways a source device determines the IP address of a destination device is through domain name service, in which an IP address is associated to a domain name. End devices on an Ethernet network do not accept and process frames based on IP addresses. Rather, a frame is accepted and processed based on MAC addresses. Now we're going to talk about the Address Resolution Protocol. When a packet is sent to the data link layer to be encapsulated into a frame, the node refers to a table in its memory to find the data link layer address that is mapped to the destination IPv4 address. This table is called the IRP table or the IRP cache. The ARP table is stored in the RAM of the device. Each entry of the ARP table binds an IP address with a MAC address. We call the relationship between the two values a map. It simply means that you can locate an IP address in the table and discover the corresponding MAC address. There are two ways that a device can gather MAC addresses. One way is to monitor the traffic that occurs on the local network segment. As frames are transmitted on the network, the device populates the ARP table with address pairs. Another way to get the MAC addresses is to send an ARP request as shown in the picture. An ARP request is a layer to broadcast to all devices in the Ethernet LAN. Since this is a broadcast, all nodes on the Ethernet LAN will receive it and look at its contents. The node with the IP address that matches the IP address in the ARP request will reply. The reply will be a unicast frame that includes the MAC address that corresponds to the IP address in the request. This response is then used to make a new entry in the ARP table of the sending node. Entries in the ARP table are timestamped in much the same way the MAC table entries are timestamped in switches. If a device does not receive a frame from a particular device by the time the timestamp expires, the entry from this device is removed from the ARP table. If no device responds to the ARP request, the packet is dropped because a frame cannot be created. This encapsulation failure is reported to the upper layers of the device. If the device is an intermediary device like a router, the upper layers may choose to respond to source host with an error in the ICMPv4 packet. All nodes must be delivered to a node on the local network segment. If the destination IPv4 host is on the local network, the frame will use the MAC address of the device as the destination MAC address. If the destination IPv4 host is not on the local network, the source node needs to deliver the frame to the router interface, that is the gateway or next hop used to reach the destination. The source node will use the MAC address of the gateway as the destination address for frames containing an IPv4 packet addressed to hosts on other networks. The gateway address of the router interface is stored in the IPv4 configuration of the hosts. When a host creates a packet for a destination, it compares the destination IP and its own IP address to determine if the two IP addresses are located on the same layer 3 network. If the receiving host is not on the same network, the source uses the IRP process to determine a MAC address for the router interface, serving as the gateway. For each device, an ARP cache timer removes an ARP entry that has not been used for a specified period of time. The timer differs depending on the device and its operating system. Commands may also be used to manually remove all or some of the entries in the ARP table. After an entry has been removed, the process for sending an ARP request and receiving an ARP reply must occur again to enter the map in the ARP table. There are two issues for the ARP. Overhead on the media and the security. Overhead on the media refers to the situation in which a large number of devices were to be powered up and all start accessing network services at the same time. There could be some reduction in performance for a short period of time. With security, we refer to the cases in which ARP spoofing or ARP poisoning techniques are used by attackers to inject wrong MAC address associations into a network by issuing fake ARP replies. This can cause the frames to be sent to wrong places. Segmentation is a technique used to prevent these common issues. The segmentation of a line is dividing the line into independent collision domains. Each port on a switch represents a separate collision domain and provides a full media bandwidth to the node or nodes connected on that port. Now we're going to talk about switching. A layer 2 LAN switch performs switching and filtering based only on the OSI data link layer MAC address. A switch is completely transparent to network protocols and user applications. A layer 2 switch builds a MAC address table that it uses to make forwarding decisions. Switches use MAC address to direct network communication through the switch fabric to the appropriate port towards the destination node. The switch fabric is the integrated circuits and the accompanying machine programming that allows the path through the switch to be controlled. For a switch to know which port to use to transmit a unicast frame, it must first learn which nodes exist on each of its ports. A switch determines how to handle incoming data frames with the following procedure. Step 1. The switch receives a broadcast frame from PC1 on port 1. Step 2. The switch enters the source MAC address and the switch port that received the frame into the address table. Step 3. Because the destination address is a broadcast, the switch floats the frame to all ports except the port on which it received the frame. Step 4. The destination device replies to the broadcast with unique frame address to the PC1. Step 5. The switch enters the source MAC address of the PC3 and the port number of the switch port that received the frame in the address table. The destination address of the frame and its associated port is found in the MAC address table. Step 6. The switch can now forward frames between source and destination devices without flooding because it has entries in the address table that identify the associated ports. Switches can operate in different modes that can have both positive and negative effects when forwarding Ethernet frames on a network. One of the most basic settings of a switch is the duplex setting of each individual port connected to each host device. A port on a switch must be configured to match the duplex settings of the media type. There are two types of duplex settings used for communications on the Ethernet network: half duplex and full duplex. Half duplex communication relies on unidirectional data flow where the sending and receiving data are not performed at the same time. Half duplex communication implements CCNA1v5 to help reduce the potential collisions and detect them when they do happen. In full duplex communication, data flow is bidirectional so that it can be sent and received at the same time. This support enhances performance by reducing the wait time between transmissions. Most switch devices now support the MDX auto interface configuration command in the CLI to enable the automatic medium-dependent interface crossover feature. When enabled, the switch detects the required cable type for Copper Ethernet connections and configures the interface accordingly. Therefore, you can use either a crossover or a straight-through cable for connections to a copper port on the switch, regardless of the type of device on the other end of the connection. Switches used to use one of the following forwarding methods: store and forward switching or cut-through switching. In store and forward switching, when the switch receives the frame, it stores the data in buffers until the complete frame has been received. During the storage process, the switch analyzes the frame for information about its destination. In this process, the switch also performs an error check using the cyclic redundance check trailer portion of the Ethernet frame. In cut-through switching, the switch acts upon the data as soon as it is received. Even if the transmission is not complete, the switch buffers just enough for the frame to read the destination MAC address so that it can determine the port to which it has to forward the data. There are two variants of cut-through switching. The first one is fast-forward switching that offers the lowest level of latency. Fast-forward switching immediately forwards a packet after reading the destination address. Because fast-forward switching starts forwarding before the entire packet has been received, there may be times when packets are relayed with errors. The other one is fragment-free switching. This switch stores the first 64 bytes of the frame before forwarding. Fragment-free switching can be viewed as a compromise between store and forward switching and fast-forward switching. When selecting a switch, it is important to understand the key features of the switch options available. The forwarding rate defines the process capabilities of the switch by rating how much data the switch can process per second. Switch product lines are classified by the forwarding rates. Entry-layer switches have lower forwarding rates than enterprise-layer switches. Other considerations include whether the device is stackable or non-stackable, as well as the thickness of the switch and port density, or the number of ports available in a single switch. The port density of a device can vary depending on whether the device is a fixed configuration device or a modular device. The fixed configuration switches are, just as you might expect, fixed in their configuration. This means that you cannot add features or options to the switch beyond those that originally came with the switch. Modular switches offer more flexibility in their configurations. Modular switches typically come with different size chassis that allow for the installation of different numbers of module line cards. In addition to determining the various switch form factors, it may also be necessary to choose between a Layer 2 line switch and a Layer 3 switch. A Layer 2 switch performs switching and filtering based only on the OSI link layer MAC address and depends upon routers to pass data between the independent IP subnetworks. A Layer 3 can also use IP address information instead of only learning which MAC addresses are associated with each of the ports. It can also learn which IP addresses are associated with its interfaces. This allows Layer 3 switches to perform Layer 3 routing functions without reducing the need for dedicated routers on LAN. That's all for this chapter. Thanks for watching.